Remember I said okay, sorry guys, 5 minutes late. So today we will continue and hopefully finish the lecture 8. And I think we are ready for the midterm. And the rest of the time we will focus on the review lectures and maybe go over the homework problems together. So lecture 8 is a very interesting and fundamental topic on sampling. And sampling is a very fundamental, and it's also the core topic of information theory, communication, and signal processing. So here we are looking at how to sample given a continuous signal. First of all, how to model the sampling process using the languages, signal processing languages that we introduced in this course. And also, once we have the sample signal, how do we understand the spectrum of this sample signal? And in particular, we want to understand what information do we lose, or under what conditions can we hope to recover the original continuous time signal from the sample signal. And turns out that the key is a concept called bandwidth that we introduced in the last lecture. So as long as the underlying continuous time signal has a limited band in the frequency domain, we can always hope for a perfect recovery if we do the sampling fast enough. So let's briefly review the setup that we introduced last time. So we have a underlying continuous time signal xt. And to do the sampling, we will multiply the signal by a sampling mask, which we call the impulse train signal. And it is denoted as PT. So PT is basically a bunch of impulses that are periodically located on the time axis. And here, this capital T is basically the sampling period that we are looking at. So depending on how fast you want to sample, we will use different impulse trains and multiply it with the underlying signal. So after this multiplication, we obtain this sample signal. It's a product of the two. And this figure illustrates the process. We have this continuous time signal, we have this impulse train signal, and then we multiply them together, and then we will obtain the sample signal. So it's a bunch of, again, it's still impulses, but each of the impulse will be scaled by the corresponding signal magnitude at the corresponding time location. Okay, and then after some derivations, we showed that the spectrum of the sample signal is highly related to the spectrum of the underlying continuous time signal in the following way. So the spectrum of the sample signal is given by 1 over T summation over K of the spectrum of the original continuous time signal. And all these xj omegas are different copies of the original spectrum, and each of the copy is shifted with a certain frequency shift. So here, this omega s is given by 2 pi over T. Is called the sampling angular frequency. So we can see that we are shifting the original spectrum to different locations in the frequency domain, and the period that we are looking at is based on the sampling angular frequency. Therefore, based on this relation, we can visualize the spectrum of the sample signal once we are given the spectrum of the continuous time signal and the sampling frequency. So this is an example that we went through last time, where we assumed the spectrum of the original signal is given by this triangle, centered triangle. And the bandwidth of the signal is assumed to be omega m. Now for this signal, we assume that we are sampling this signal at a sampling frequency omega s. And then this is a visualization of the spectrum of the sample signal based on this equation. So first of all, we scaled all the spectrum magnitudes by 1 over capital T. So this is a very simple magnitude scaling. And then for this infinite summation, we are basically copying the original spectrum and pasting the spectrum at different periodic locations. And in particular, the gap between two consecutive copies is omega s is determined by the sampling frequency. So depending on the relation between the sampling frequency and the bandwidth of the underlying signal, we will have two scenarios. The first scenario is when the sampling frequency is bigger than 2 times the bandwidth of the signal. In these cases, we will see that all the different copies, they are non-overlapping with each other. So there's no overlap among them. And in this case, the information of the spectrum of the original signal is perfectly preserved. So we can simply, so once we have this sample signal, to recover the original signal, we can simply do a low pass filtering. So you apply a low pass filter to this signal and filter out any one of the copies of this spectrum. And then you can rescale the spectrum by multiplying it by T, capital T. After that, you basically recover the exact original spectrum. And from there, you do an inverse Fourier transformation, you can get original signal. Okay. So the key is that in this case, there's no overlap among all these copies. So this is called the Nyquist sampling rate. So as long as we are sampling at 2 times higher than 2 times the bandwidth of the signal, there's no overlapping among these copies, and we can hope for a perfect recovery. Now, on the other hand, if the sampling frequency is lower than this threshold, then these different copies will be overlapping with each other, and then the spectrum will be in general, they will be distorted, and consequently we cannot recover the original spectrum anymore. Okay, so this is the most important conclusion from this observation. Okay. The Nyquist rate. So if I give you a signal and I suppose you are given the spectrum of this continuous time signal, you should be able to identify the Nyquist sampling rate for this signal. It's basically 2 times the bandwidth. And let's look at this very important example, which is a bunch of sinusoidal signals. And we can have a more intuitive understanding of this Nyquist sampling in this example. So let's do a sampling on 3 different signals, X1, X2, and X3. So they are given specifically as follows. So X1 is cosine 40 pi t, okay? It's a very specific signal. X2 is cosine 160 pi t, and X3 is cosine 240 pi t. Now we can see that their angular frequency are different, which means they have different frequencies and different fundamental periods. And then let's sample all the 3 signals at the same sampling rate. So suppose we sample all these 3 signals at 1 over capital T. This is the sampling frequency in hertz at 100 hertz, meaning that we take 100 samples per second on these 3 signals. And then we can, so let's actually compute all the basic informations first. So X1t is cosine 40 pi, which means the omega 1 angular frequency is 40 pi by definition, and T1 is 2 pi over omega 1. The fundamental period. So it's 2 pi over 40 pi is 1 over 20. And similarly, X2 we got this, and T2 is 2 pi over omega 2, which is 1 over 80. So this one has higher frequency, which means a smaller fundamental period. And the third signal, we have the fundamental period is 2 pi over 240, which gives 1 over 120. So x1, if this is x1, x2 is higher frequency, and x3 is even. So this is an illustration of these three signals. Okay. But now we are sampling all the three signals at the same sampling rate. Okay. The sampling rate is 1 over t is 100. So Ts, okay, 1 over t is 100. So the sampling angular frequency is 2 pi over the sampling period. 2 pi over t. Now 1 over t is 100. So the omega s is 200 pi. 200 pi. 2 pi times 100, 200 pi. So this is the angular sampling frequency that we are looking at. Okay. And now let us try to figure out, plot the spectrum of the sampled signal for all the three x1, x2, and x3 signals. So first of all, from the Fourier transform, right, from the table, we already know the Fourier transform. We know the spectrum of cosine signals. So let's take x1 as an example. Okay. So here are two things. First, we will visualize. Okay, let's first plot the spectrum of x1t. So this is x1 j omega. Right. So given x1t cosine x1t as cosine 40 pi t, we can plot this. We can find out the Fourier transform and plot the spectrum. Now from the table, we know from the standard results, we know this cosine signal, it corresponds to a pair of impulses in the spectrum corresponds to a pair of impulses in the frequency domain. And they are located at symmetric locations at 40 pi. So if you visualize that, you will have this. One is at 40 pi, the other one is negative 40 pi. And then we can further. So this is the given spectrum of x1t, and then we also know the omega s, the sampling angular frequency. So we can further visualize, plot the spectrum of the sample signal. Let's do it here. So I probably need to move these two arrows closer so that I can have space to reach 240. Let's say this is 40 pi, this is negative 40 pi. Okay. I move them closer. So this is x1 j omega. So we want to visualize, now we want to look at x1 p j omega, okay, the corresponding sample version. And how do we do that? Well, we follow this equation. It's basically, first of all, we can ignore the scaling part because it's just it doesn't change the change the time scale or the frequency scale, only the magnitude scale. It doesn't matter. So we can just focus on the summation part. Well, the summation part basically says you are copying the original spectrum at different locations. Now the when k equals to 0, this is the first copy. Now the first copy is basically the original spectrum. So you will have the first copy right here. And of course, because of this 1 over t, so the magnitude will be scaled accordingly. Okay, so this is the first copy. And then you look at the second one, like for k equals to 1, the second copy, if k equals to 1, you are shifting this spectrum to the right by omega s. And now omega s is given by 200 pi. So you are shifting these two arrows to the right by 200 pi. That will give you the second one. So you do the second one, shifting to the right by 240 pi. This one becomes 280 pi, and this is 200 pi. So you have two arrows right here, and this is 280 pi. This is 200 pi. And correspondingly, for k equals to -1, you have these two. Okay, so these are the first 3 copies, and the rest of you have infinitely many of these copies. So you can just plot the first 3. And you can already tell that there's no overlap between these copies, right? This is this one, the first one, the second one. They are not overlapping with each other. So in this case, you conclude that there's no aliasing, and you can perfectly recover the original signal. So which means that if you sample this x1t at 200 pi at this angular frequency, it is sufficient. This sampling frequency is sufficient to recover the original signal. And you can also check this by the Nyquist criteria. So you look at omega s is 200 pi. And then you look at 2 times the bandwidth. Now the bandwidth omega 1, if you look at this spectrum, right? Looking at this spectrum, the bandwidth is 40 pi, right? Because it's symmetric, and so the width of the band is 40 pi. So this is the bandwidth, this is the sampling rate. And the Nyquist criterion compares the sampling rate with 2 times the bandwidth. Now you can easily see that omega s is greater than 2 times the bandwidth, which is 80 pi. And therefore, you can conclude that in the spectrum of the sample signal, there's no aliasing. And we indeed verify this by plotting out the spectrum. Okay, so this one is good. This one is good. So 100 samples per second is enough to preserve all the information for X1T. So that is the conclusion here. So this is for X1T. Now for X2T, we can do the same thing. X2T is cosine 160 pi. So the omega 2 is 160 pi. 160 pi, right? So, and you can, first of all, you can apply the Nyquist criteria to draw the conclusion. So the sampling rate is 200 pi, is given, and 2 times omega 2 is 320 pi. And we can see that this is less than equal to 2 times the bandwidth, which means this sampling rate is not sufficient for preserving all the information of the in X2T. And next, let's visualize what happens in the sample signal in the spectrum domain. So first of all, we follow exactly the same steps as we did in the X1T example. Right? We first plot the spectrum of X2T, and this is very simple. Again, it's a pair of impulses in the frequency domain. They are now located at 160 pi. And then we start looking at the spectrum of the sample signal. Okay, so again, it's basically the same steps. So for the first copy, it's basically the original spectrum. Right, again, following this equation, when k equals to 0, that's the first copy, which corresponds to the original spectrum. So it's the same thing here. But now, starting from second one, we need to be a little bit careful. So the second one is shifting this copy to the right by when k equals to 1, to the right by omega s. Omega s is 200 pi, still 200 pi. So it's shifting these two arrows to the right by 200 pi. So this one, 200 pi, goes to 360 pi. And this one plus 200 pi goes to 40 pi. But 40 pi is to the left of this arrow. So you will see that after shifting, you end up with these two arrows. One is 40 pi. And the other is 360 pi. And then you have, when k equals to -1, you have these two arrows. So I will not, okay. 45, 360, -40 pi. And the rest of the copies follows the same idea. But here you can already tell that these different copies are indeed overlapping with each other. Right? So the green one is here, and it is overlapping with the first copy, the red one. This means if you let's say if you want to apply a low pass filter and filter out the first copy, and you want to apply the low pass filter and filter out this pair of red arrows. This is the first copy. If you do that, you will see that if you apply low pass filtering, you will have 4 arrows, right? 2 from the first copy and another 2 from the second and third copy. And that will give you a wrong estimation of the original spectrum. Okay, so this shows that if you do not follow the Nyquist criterion, you will have some distortions in the spectrum, and you cannot recover a signal by low pass filtering. Okay, so this is consistent with the Nyquist criteria. And moreover, okay, we have another one, X3, so you can do the same thing. So here I will skip it, and maybe we can quickly draw the conclusion, because X3 has an even higher frequency, right? Which means it is the Nyquist criterion 2 times the bandwidth is even higher. So again, this sampling frequency will not be able to satisfy the Nyquist criteria. So you will have aliasing in the resulting spectrum of the sample signal. And we can quickly draw the spectrums. So X3 has a spectrum located at 240 pi. Great. This is from its own omega. And then we do sampling at omega s, which basically means for the first copy we have the same spectrum. And the second one we shifted to the right by omega s. Omega s is 200 pi. So here we have this one shift by 200, we get -40. And this one shift by 200, we get 440. Okay, and then you have the other one right here and here. So this is 40 pi. And again, you will see that they are overlapping with each other. And if you plot more copies, you will see that between these 2 arrows, you have more than two arrows in between them that are generated by the other copies. Okay. So basically, for X2 and X3, this sampling rate does not meet the Nyquist criteria. So, and which means the aliasing will occur in the frequency domain. And actually, these 3 examples are artificially designed so that they have the following interesting phenomena. So first of all, if you look at the spectrum of the sample signal, you will find that, okay, this is our spectrum. This is the first spectrum of the sample signal of X1, right? And this is the second one. This is the third one. Now we have seen that the first one, they have no overlapping. They are separated. The second one, we do have some overlapping in between. And third one, we have even more overlapping between them. However, if you look at the locations of these arrows very carefully, and if you plot out all the copies, you will find that all these three spectrums, they are exactly the same. For example, here you have arrows located at 40 and negative 40 pi, and next one is 200 pi, 280. And if you look at this one, you have arrows located at 40 pi, negative 40 pi. Which one? The first one? Oh, yeah, I should shift by 200 pi. Yeah. Yes. Yeah, omega s is 200 pi. So this is 240 and 160. Yeah. And then you will see that, right. So you can see that we have two arrows at 40 pi and negative 40 pi. Here we have two arrows at, okay. These two should be switched with each other. This is negative 160, this is negative 240. We have two arrows at 160 pi and negative 160 pi, right? And if you look at the second one, we have two arrows at 40 pi, negative 40 pi, and another two arrows at 160 pi, negative 160 pi. Now, if you plot all the copies, you will see that these two spectrum are identical. And if you further look into the third spectrum, you will see again they are identical. We have arrows at 40 pi, we have arrows at 240 pi. If you go to k equals to 2, that one will generate arrows at 160 pi. Okay. So in the end, if you plot out the entire spectrum of all these sample signals, you will find that they are the same for the three signals, which means when you sample the three signals at this sampling rate, they happen to generate the same discrete signals. And it might be hard to visualize this here, but to get you a very intuitive idea, let's say this is x1t, and the other one x2t, the frequency is higher, so we have more periods. And so let's suppose this is x2t. And I will not draw x3t here, which will make the figure messy. So what happens is that you will find that very interestingly, if you sample these three signals at 100 samples per second, those samples will always be sampled at their intersection points. Like here. I mean, this figure may not be that rigorous, but all those sample points will happen to be their intersection points. And this goes back to our original discussion at the beginning of this lecture, where we are given, if we are given a discrete signal, so if we are given such a set of discrete signal, then we can draw infinitely many candidates candidate continuous time signals that interpolate all these discrete samples, right? Just like this example, from these sample signals, we find that X1, X2, and X3, all these signals perfectly interpolate all these discrete samples. However, only one among these three candidate signals, only one of them satisfy the Nyquist criteria. So, which means if you know that your underlying signal has a band less than 40 pi, then X1T is the only option that you can have. So that's why you can have perfect recovery for band limited signals. You need to always limit the bandwidth so that you can rule out all the other high frequency candidates.
A quick question.
Yes.
What did the intersections represent again?
The intersections represent the samples you queried at this sampling rate. So for example, yeah. So if you look at the black line, this is X1T, and then if you draw the samples, if you sample this signal at 100 samples per second, you will pick out these purple points. Let's suppose these are the samples that you draw. And if you do the same thing for X2T, you will find that amazingly the sampling points that you draw is always identical to the samples that you queried from X1T, because all the sample points happen to be at the intersection points of these two signals.
Oh, okay, thank you.
I think it might be it's very hard to visualize. I don't know if I have a figure here to visualize this. Let me quickly check. I remember somewhere. Yeah, you can visualize. You can plot this in MATLAB and verify by yourself. You can plot the X1T and X2D and also plot out all the query samples, and you will see that they are exactly located at the intersection points, which means if you query these discrete samples on both of these two signals, you will end up with the same discrete signal. And same for the X3T. One explanation to this is that because the sampling frequency is 200 pi, so you can kind of think about, like, for X2T, you can subtract 200 pi subtract 160 pi is exactly 40 pi, right? And 240 pi subtract 200 pi is exactly 40 pi, which means if you query samples every 200 pi, then all these three signals, they will touch with each other. They will intersect with each other. They have the same values at those discrete points. Okay, so this is it's kind of a magic number for these three signals. Okay, so this example shows that first of all, we verify the Nyquist rate. Right? If the Nyquist criterion is not satisfied, then the spectrum will have aliasing. And it also tells us that for a given discrete sequence, you can always have a multiple candidate signals that interpolate among those points. But if you follow the Nyquist criterion, there's only one signal that can satisfy the Nyquist rate. And this is the only solution that you can find if you want to do a perfect recovery. Okay. So this is the Nyquist criterion. And next we can briefly talk about how to perfectly reconstruct signal from the sample signal. It's basically a low-pass filtering. So this is again, this is a picture illustrating xpj omega, the spectrum of the sample signal. And in particular, in that infinite summations, this one is the first copy, right? When k equals to 0. And these are all the rest of the copies. So the idea is that suppose your sampling frequency is higher than the Nyquist rate, so that all these copies are not overlapping with each other. And then we can do a low-pass filtering to recover the original signal. So specifically what you do, you can, for example, the easiest way is to filter out the first copy, this one, the centered copy, because it is centered, and filtering out all the rest of the copies. And to do that, you just need to apply for a low-pass filter. Apply a low-pass filter to the entire spectrum. And from this picture, you can see that the low-pass filter, of course, it has to be a rectangle filter, a low-pass filter. And the cutoff frequency must be satisfying a certain criterion. Now, from the figure, you can see that this rectangle has to cover the entire first copy, and also do not touch the second and the third copy. So to satisfy this criterion, the cutoff frequency omega c must satisfy, first of all, it must be greater than omega m, the bandwidth of the first copy, so that this rectangle will cover the entire first copy. And at the same time, it has to be less than equal to omega s minus omega m, which is the ending point of the left-hand side of the second copy. So the cutoff frequency must be lower than that one, so that this rectangle will not overlap with the second or the third copy. So if you design a low-pass filter with such a low cutoff frequency and apply it to this spectrum, then you can perfectly filter out the centered copy, the first copy. And this is exactly the spectrum of the original signal, except for a magnitude scaling. Okay. So specifically, what you do is this: you have your sample signal, and this is the spectrum of the sample signal. And then you design a low-pass filter H. You design a low-pass filter such that the cutoff frequency omega c satisfies this inequality, like we discussed in the previous slides. And then you apply, by multiplying these two spectra together, you are basically applying the filter to this spectrum. And then the resulting spectrum is the centered copy. And to satisfy this inequality, of a special choice is to set the cutoff frequency to be omega s over 2. Is to have 1 over 2 times the sampling frequency. Because you can see that this choice satisfies both the lower bound and upper bound. Right, so you have two inequalities here. So let's explain this. So first of all, your cutoff frequency must satisfy these two inequalities. And at the same time, in this case, you know that the sampling rate is greater than 2 times the bandwidth. Combine these two inequalities, you can verify that omega c 1/2 of the sampling rate is a feasible solution. Right, because from this inequality, we know omega m is less than 1/2 the sampling frequency. So if you set the cutoff frequency to be this value, then this will be greater than omega m. Then you can also verify the right-hand side. Also, it's also feasible. So in the end, this is one choice that you can take. Okay, so this is the filtering equation, low-pass filtering in the frequency domain. Now we can translate this back into the time domain, which means that you have your sampled signal, XPT, and then in order to apply this low-pass filter, you need to figure out the corresponding signal, HT. You do an inverse Fourier transform, figure out the corresponding HT, and then this multiplication becomes convolution in the time domain. So this would be the equation, that low-pass filtering equation corresponding to the time domain. Okay, so here XPT is your sample signal, and HT is the inverse Fourier transform applied to the low-pass filter. And we know that HT is a sinc type signal because inverse transform applied to a rectangle spectrum gives a sinc type signal. Okay, and now we keep going, and because XPT is given by such a infinite summations, XPT is a sample signal. So XPT is given by this one from the previous slide. So you plug it in, so it's XPT convolution with HT. And now this HT convolution with delta impulse signal. This is a very simple convolution. And we know that it gives H evaluated at T minus and capital T. Okay. It's a convolution property of the impulse signals. So what you have is that you conclude that after low-pass filtering, this is your reconstructed signal. Okay. Your reconstructed signal is basically your discrete samples. These xn are the discrete samples you sampled from that continuous time signal. Is this xn multiplied by this low-pass filter, shifted to low-pass filter, and then doing a summation over all the samples. Okay, and this is to show exactly the analytical expression for HT. So this is the low-pass filter in the spectrum domain. It's a rectangle because it's a rectangle spectrum in the frequency domain. And from the Fourier transform, we know that this spectrum corresponds to such a sinc type signal. Omega ct over pi sine omega ct over omega ct. Okay, so this is the HT, the analytical expression for the HT. And then, okay, you plug in this HT into here. So you finally conclude that your reconstructed signal is given, okay, your underlying continuous time signal can be reconstructed from your discrete samples in this way. Okay, think about this equation. You have your discrete samples xn queried from that continuous time signal. And how do you reconstruct the underlying signal? Well, you just, at each discrete sample xn, you will need to multiply it by such a sinc type signal. Or you can understand this as, this is a shifted sinc type signal to the location n capital T. And you will scale such a sinc signal by xn. And at the end, you will superpose all these scaled sinc type signals together in order to reconstruct your underlying signal. So xn is a discrete samples and T is a sampling period. Now this is an illustration of this reconstruction process. You have your xt, this is the underlying continuous time signal. And you do a sampling at a Nyquist rate, so you have these red dots. So these are the discrete samples that you draw. So in the end, you have this xn. This is a discrete signal, right? So sampled discrete signal. Now, if your sampling rate is above the Nyquist criteria, then you follow this equation. You can reconstruct the underlying signal. So what you do is basically at every sample, for example, at this discrete sample, you will, if you look at, go back to this expression, right? At each sample xn, you will have a sinc type signal. So this sinc signal is centered at the same location because it's shifted by n capital T, right, with the same index n. So you have a sinc signal located at the same location, and then the difference is that these sinc signals will be scaled by the value of your discrete sample xn. So for example, if you look at this one, this is a discrete sample of your discrete signal. And then right at this location, you look at this blue curve, you have a sinc signal that scaled by, centered at this location and scaled by the magnitude of this discrete value. So it looks like such a sinc type signal. And if you look at here, negatively, you have the discrete sample has a smaller magnitude. So right here, you have another sinc signal that is centered at this location, and the magnitude is scaled by such a discrete value, the discrete sample. So it is a lower sinc signal with a lower magnitude. So at every such discrete sample, you generate such a scaled sinc signal centered at this location. And in the end, you add up all these green lines. Okay? Each green line is a sinc signal. You add up all these sinc type signals. Their summation, their superposition will generate this blue signal, which is exactly the original continuous time signal. Right, so this is the illustration of the reconstruction process. We follow the mathematical derivations. So we basically do a low pass filtering, and the inverse transform. Okay, now if you look at this equation, you can see that as long as you sample the signal beyond the Nyquist rate, okay, as long as this sampling period is small enough, so you are sampling the signal at a sufficient frequency, you can always reconstruct the same signal by this equation. And so which means, now suppose you are sampling at 100 times the Nyquist rate, then you will have much more discrete samples. And also this capital T will be much smaller, but you can still, you can always reconstruct the same signal following this equation. So depending on your sampling rate, sampling period, or sampling frequency, this xn will change, right? So in this figure, we are sampling the signal at 1 samples per second, right? If the x-axis is time, is a time axis with each unit, the unit is denoted by second, then we are taking 1 samples per second. And you can take 2 samples per second, which will definitely satisfy the Nyquist rate. Then you will have more discrete samples here. And again, at each discrete samples, you generate such a sinc type signal. And their summation will give you the same underlying true signal. So this is an illustration of the low pass filtering process in the time domain. But in the frequency domain, this is very easy to understand. You just apply a rectangle low pass filter to that. You just apply this rectangle low pass filter to this periodic spectrum and filtering out only the centered copy of the spectrum. Okay. So any questions regarding this part?
Is the interpolation the part that scales the magnitude back because of the inverse transform? Sorry, does that make sense?
You mean the
when we have the
for this 1OT factor?
Yes.
Yeah. Oh, I think this is okay. Right. Okay. I think just I think I missed this part. Yeah. When you do the low pass filtering, right? Because in the sampling process, this spectrum is scaled by 1OT. So that's why you have 1OT here. And then when you design low pass filter, you need to design it so that the response is given by capital T, right? So that you can cancel out this scaling factor, right?
Oh, okay.
Yeah, and then this is reflected by right here. So you need to design this low pass filter with capital T response. So and consequently, in the HT, this signal is also scaled by capital T. Yeah, I think this explains why there's a capital T here.
Oh,
So
I
this
see.
will compensate for the 1/T factor.
Okay, thank you.
Yeah, so this is a standard low pass filter. The ideal low pass filter. Okay, And this is a Nyquist theorem. I think we all know the statement. Basically, if you have a band limited signal with bandwidth omega m, so this bandwidth is expressed in terms of angular frequency. The unit is Res. It's not hertz. So if you have bandwidth omega m, then in order to preserve the information in the sampling process, your sampling frequency must satisfy this Nyquist criteria. Sampling angular frequency must be higher than 2 times the sampling bandwidth. So 2 times the sampling bandwidth is known as the Nyquist sampling rate. And if you look at the statement carefully, okay, now this is the forward statement. Forward meaning the sampling process. So in order to preserve the entire information of the signal, you need to sample it at least at the Nyquist rate. And the backward process is right here, which corresponds to the reconstruction process. Meaning that if you do Nyquist sampling, if you sample at a Nyquist rate, then you will be able to recover the signal by low pass filtering. This is what this paragraph says. And this opens another question. So I think the last picture is okay. So this opens another question about another fundamental question in signal processing domain. The question is here we are considering recovering the signal by low pass filtering. This is a very specific approach for signal recovery. So the question is, are there other sampling schemes that you can recover this, so that you can sample signal at a much lower frequency than the Nyquist rate, and then you will still need to be able to recover signal through other recovery approaches different from the low pass filtering. And the answer is yes, we indeed have lots of other sampling schemes. Well, you can sample the signal at a much lower frequency than the Nyquist rate. But in the reconstruction process, you cannot apply low pass filtering. Instead, we will need to do some mathematical programming to reconstruct the signal from the discrete samples. So those are called the compressed sampling. And you may learn that in some advanced courses in signal processing. Yeah. So the general idea is that if you look at the Nyquist sampling theorem, we leverage the band limited structure, right? That's the key structure that we are looking at. We are looking at the bandwidth of the signal. And then, so that is in the sampling process. And in the reconstruction process, correspondingly, we are looking at the low pass filtering. Because low pass filtering exactly works on a continuous band. So in the forward process, we are looking at band limited signal. And in the backward process, we recover the signal by low pass filtering. And there exist other more efficient sampling approaches. Well, in the forward process, in the sampling process, we look at other classes of signals, not just band limited signals. A very interesting class of signals is sparse signals. So all the signals that we encounter in practice, images, audio signals, they have sparse representations in some domain. Fourier domain or other domain. So by leveraging the sparsity, we can, in the reconstruction process, we can design other algorithms to reconstruct signal. And leveraging this structure sometimes can sometimes only require very few samples of the original signal. Yeah. So here, the Nyquist sampling is a very it's one of the many popular sampling schemes that we are looking at in the signal processing area. Okay, so we have a question: does the accuracy of the data go up as you get higher sampling rates, or is the Nyquist sampling rate accurate enough? From the statement, Nyquist sampling is enough. Yeah, so you don't have to go beyond that. As long as you are sampling at this frequency, you can perfectly recover the signal. But sometimes, but in practice, if you do the reconstruction process, you always want to, intuitively, if you sample the signal, okay, although Nyquist rate is a hard threshold, right? Once you go beyond that, you can perfectly recover signal. But in practice, it's always, if the resources allows, it's always better to query more samples of the signal. So you have, because sometimes when you do low pass filtering, for example, the low pass filter may not be perfect. There are other engineering issues in practice where more samples can definitely help in reducing those errors. But technically or mathematically speaking, in an ideal case, Nyquist sampling rate is enough for a perfect reconstruction. Okay, and this is a simple example. We can briefly go over the first one. So we have an input signal given as follows. It's xt, and then so the first question is find the Nyquist sampling rate of xt. Well, it's very simple. You identify the bandwidth of the signal, and then multiply by 2. That is the Nyquist rate. So looking at the expression, looks like the bandwidth is given by the highest component, sinusoidal component. So the bandwidth is 6 pi. 6 pi multiplied by 2 is 12 pi. So that is the Nyquist rate. And then choose the cutoff frequency as half the sampling rate. Discuss the 2 cases of sampling period. Okay. So basically, here we are looking at this system where we first sample this signal at a certain frequency. And then once we have the sample signal, we want to do a low pass filtering and try to reconstruct the signal. And here we consider 2 different sampling frequencies. One is pi over omega n, one is 4 pi over omega n. The first one, you can verify that this means we are sampling the signal at 2 times the Nyquist rate. So definitely we can do perfect recovery. The second one, we are sampling at 1/2 of the Nyquist sampling rate. So it does not satisfy the Nyquist criteria. So we will sample the signal at these 2 different frequencies, and then in the recovery phase, we will design that low pass filter with a cutoff frequency given by 1/2 of the sampling rate. So I think the question is, what will we get in these two cases on the output side? So we don't have enough time to go over this one. I think we will leave it to the next lecture. But I think you can think about this one and try to figure out by plotting out the spectrum of the sample signal and also plotting out this low pass filter, then you will find out what is the part of the spectrum that is being filtered out. And from there, you can understand the output signal. Okay, so I will stop here, and after the class, I will hold office hours. In the next week, we will do a review lecture, and for the rest of the time, we will leave it for discussion and office hours. Okay. Okay, I will see you guys next week. Have a nice weekend.